Random variables, section 4.0. A random variable is a variable that takes on values with specified probabilities. Example 1a, among heterosexual married couples, the probability that the woman is hypertensive is 0.2. The probability the man is hypertensive is 0.3. Assume that the woman's blood pressure is independent of the man's blood pressure. Let x be a random variable representing the number of hypertensive adults in the couple. Part A, find the mean or expected value of x. So the proportion of women that are not hypertensive is going to be 1 minus 0.2, which would be 0.8. Proportion of men that are not hypertensive, 1 minus 0.3, which is 0.7. And we can either make a tree or a table to fill out these probabilities. So I'm making the a 2 by 2 table here. The first row is the men are hypertensive. Second row, the man is not hypertensive. First column, the woman is hypertensive, and the second column, the woman is not hypertensive. So the bar indicates not. So we can start with our row totals and column totals. So the row total for the M row is going to be 0.3. That's the proportion of men that are hypertensive. The row total for the M bar row is 0.7. That's the proportion of men that are not hypertensive. The column total for the W column, 0.2, and the column total for the W bar column is 0.8, and the grand total is 1. 0.2 plus 0.8 is 1, or 0.3 plus 0.7 is 1. Okay, so because we're assuming independence, we can multiply to get these probabilities. So it's going to be column times row. So this box here, it's actually, this is the M row of the W column. So the man is hypertensive and the woman is hypertensive. This one here, the M row, W bar column, that's the man is hypertensive, the woman is not. Here we have the M bar row, W bar column. No, just the W column. W column. A man is not hypertensive, the woman is. And this is the M bar row, W bar column. Neither one is hypertensive. Okay, so for this position here, again, it's the column total times the row total divided by grand total. So this is going to be 0.2 times 0.3. Well, actually, the grand total is 1, so if you want, you can divide by the grand total, but that's just equal to 1. And this is going to be 0.06. 2 times 3 is 6, and we have 2 digits to the right of the decimal. And then this one will be 0.8 times 0.3. Divided by the grand total, which is 1, so this is going to be 0.24. And this one will be 0.2 times 0.7 divided by 1, 0.14. This is 0.8 times 0.7. 0.8 times 0.7 divided by 1 is 0.56. Okay, so okay, so those are the probabilities that we need, in order to eventually find the mean or expected value. Okay, so so x is a random variable representing the number of hypertensive adults, and we want to use this box to fill in these probabilities. So the probability that neither is hypertensive, that's the M bar row and the W bar column, is going to be 0.56. That's the probability x is equal to 0. It's 0.56. And the probability x equals 1, well, there's two ways that can happen. The man is hypertensive, the woman is not, or the man is not hypertensive, the woman is. So it's going to be 0.14 plus 0.24. plus 0.24 would be 0.38. And then the probability x equal 2, they're both hypertensive. That's going to be the 0.06. The man is hypertensive, the woman is hypertensive. And if we did everything correctly, these should add up to 1. You can use that as a check. And then now we're ready to compute the mean. The mean is a weighted mean. It's weighted by the probabilities. So it's going to be the each value of x times its probability. So it'll be 0 times 0.56, which is equal to 0. 1 times 0.38, which is equal to 0.38. 2 times 0.06, and that's equal to 0.12. So if we add these up, this total here is 0.5. So the mean here's the notation. It's the Greek letter mu. It looks a little bit like a U, except this has an extra tail at the beginning. That represents the mean of a random variable. It also represents the mean of a population. And it's a sum of each of these products of each value of x times its probability. So we want to multiply each value of x times its probability, add them up, and this is the column total here. It's 0.5 adults. So on the average, we would expect within a heterosexual married couple, half an adult. Now in actuality, the values of x are not. X does not take on the value of 0.5. Either you'll have 0, 1, or 2, but on the average, you'll have half an adult that is hypertensive. And we can also compute the variance. So again, these are possible values of x, and we want, now that we have the mean, we can compute each score minus the mean, square it, multiply by its probability. So it'll be, the mean is 0.5, we know that now, so this could be 0.5, each score, 0 minus 0.5 squared, times the probability, the probability of 0 adults is 0.56, so it's times 0.56. So this is going to be 0.14. Okay, and then if x is 1, we're going to have 1 minus 0.5 squared, and the probability x equal 1 is 0.38, so it's times 0.38. I think it's with 895. .095. Okay, and then we'll have 2 minus 1.5, 2 minus 0.5 rather, squared, times, and the probability x equal 2 is 0.06, so 10.06. Okay, so 2.25 times 0.06, we get 0.135. Okay, so if we add these up, plus 0.095 plus 0.14, I get 0.37. Okay. So that's the variance. The variance is 0.37. Again, we can, here's the formula. This formula just basically tells you what operations to do in what order. So it's each score minus the mean, and then square it, times it by the probability of x having that value, and then add up all these products here, and that gives us the variance of 0.37. And then compute the standard deviation. We can take the square root of the variance, and it gets approximately 0.61 adults. That's the standard deviation. Okay, so okay, so that's basically that example. It gives you an idea of random variables, and we're going to be looking at a variety of random variables. But let me say another thing about this particular one now, before I go on to different examples. We made an assumption that the woman's blood pressure is independent of the man's blood pressure, but within a couple, it's likely that they're not. The blood pressures are not independent, because from what we know of blood pressure, it's partly affected by genetics. It's also partly affected by lifestyle, and within a couple, lifestyle includes eating habits and sleeping habits, exercise habits, and within a couple, it's likely that their habits are going to be somewhat similar, especially the eating habits, and probably also the exercise habits too, but in addition to the eating habits. But so they're probably not actually independent, but it's still useful to compute the probabilities, because we can compute the probabilities that if they are independent, and then compare it to our actual data to see how far they are from being independent. So that's so it's still some use, even though they're probably not independent. It's still useful to know what the probabilities would look like if they were independent. Okay, so this next example, it's not so much an example, it's sort of a commentary about notation. The random variable of example 1a, this is an example 1b, the random variable of example 1a took on only the values 0, 1, and 2. A random variable such as example 1a that takes on only a countable number of values is called discrete. Typically the values that a discrete random variable takes are whole numbers like 0, 1, 2, 3, 4, etc. By way of contrast, a random variable that can take on any value on an interval is called continuous. For example, if x represents a woman's blood pressure instead of the number of hypertensive adults, then x is a continuous random variable. We will learn more about continuous random variables in the next module. Example 1c, suppose now that x represents the number of students in a classroom. If the maximum class size is 12, then x is a discrete random variable which can take on the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anything between 0 and 12. Any whole number between 0 and 12. This turns up in some of the web assigned questions, and so I've gotten some questions from students about this, and what often happens is people will start with 1. They'll say, well, the possible values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But it's possible that nobody could sign up for a class. You could try to run a class and nobody would sign up. So the most common mistake there would be to leave off the possibility that x is 0. So if the maximum class size is 12, then the number of students in the class could be anywhere from 0 to 12. Example 1d. This is similar to something some of the assignments in web assign also. Discrete random variables have the property that the probabilities add up to 1. So if we're given a list of probabilities and we're missing one of them, we can figure that one out because we know these have to add up to 1. So this here we have this unknown random variable probability here for x equals 3. So x is 0, 1, 2, or 3. Probably x equals 0 is 0.3. Probably x equals 1 is 0.1. Probably x equals 2 is 0.1, but we don't know the probability x equals 3. So 0.3. Let's see if I get a better pen here. 0.3 plus 0.1 plus 0.1 plus whatever this number is plus x should equal 1. So if you add these up, this is 0.5 plus x is equal to 1. Subtract 0.5 from both sides. X is equal to 0.5. So the missing number here is 0.5. Okay, so there's a couple of exercises like that in WebAssign. Example 1e. If x represents the number of hypertensive adults within a random sample of 2 people, because these people were chosen randomly, most likely they are not related, and each independently has a chance of 0.25 chance of being hypertensive. If we assume that the proportion of people are hypertensive is 0.25. The random variable x in this situation is a special discrete random variable called the binomial random variable. So this is different from the original example because here we had a heterosexual married couple and a man and a woman within the couple, and each had a different probability of being hypertensive. But now we're just randomly choosing 2 adults, and they're not necessarily a couple, not necessarily the same, they're not necessarily different genders, so this is a different situation, and this is called a binomial random variable. And we'll later this week, or actually in a later video, we'll go over binomial random variables in more detail. But this would be a binomial random variable with sample size n equal 2. Typically, with the binomial, the sample sizes are bigger, like in the hundreds or thousands. But the sample size could be anywhere from 2 up to as big as you can imagine. But yeah, typically it's in hundreds or thousands. So we'll go over that in more detail in a later video. Okay, example 1f. Suppose now that x represents the number of children in a randomly chosen person that a randomly chosen person has in a lifetime. In some cultures, the mean number of children is 6. This random variable is discrete because it only takes on whole numbers, 0, 1, 2, 3, etc. But this is similar to a binomial, except there's no upper limit here. So this is another special random variable. It's called the Poisson random variable. It's spelled like poison, but it's pronounced Poisson. So it's similar to the binomial in some respects, but it's a different random variable because there's no upper limit on the number of children, the number of values of x. And generally the Poisson random variable represents the number of occurrences of a rare event. So even though the Poisson random variable can take on an infinite number of values, it's still considered discrete rather than continuous because there's separation between the values. For example, a person can have 1 child or 2 children, but not 1.7 children. Again, we'll go over Poisson in more detail in a later video this week. And that concludes this presentation.